talk is going to be by Vishvesh Kumar from Ghent University, Belgium, on the topic LP-LQ boundedness of Fourier multipliers associated with an harmonic oscillator. So, Vishvesh,
Okay.
please.
Yeah, thank you, Senthil, for your kind introduction. And I would like to thank organizer for this wonderful event. And it's nice to see, especially Professor Thangavalu, because he is expert of this topic. And I'm very happy that he's here. So today I will talk about LP-LQ boundedness of Fourier multiplier associated with anharmonic oscillator. And thanks to Cyan for setting the platform for LP-LQ boundedness of Fourier multiplier, especially for spherical maximal functions, which is also a Fourier multiplier. So let us start with the definition of the Fourier multiplier. So an operator on suitable space is called a Fourier multiplier with symbol sigma. If you apply the Fourier transform on the image of the function, it gives to a multiplication by a complex number to a Fourier transform of that function, where hat represent the usual Euclidean Fourier transform. And in this talk, we also discuss LP-LQ boundedness of a spectral multiplier also. So let us define a spectral multiplier. So first so yesterday we had a talk about on a spectral multiplier, and so we take a non-negative self-adjoint operator on L2X. So X is a sigma finite measure space with a spectrum containing inside 0 to infinity. Then for any function from 0 to infinity to C, using the spectral theorem, we can define the spectral multiplier, because for the spectral theorem, we decompose L as the integration over the spectral and then lambda and D E lambda, where E lambda are the spectral projections. And then using the functional calculus, we can define this operator P of L. So E lambda are the operator valued projection valued measures. So the main problem in harmonic analysis to study boundedness of Fourier multiplier or spectral multiplier, that means to find the sufficient conditions on the symbols. So two famous condition on this on the symbols is one is Hormender type condition, and second to study LP boundedness is second is Marcinkiewicz type condition. So these type of condition has been studied for a long time. It's a good tradition, and also they are very hard problems. So, and many people work in this setting. So few name it started with Hormender in 1960, and for a Euclidean case LP boundedness, then Clark-Stein, Taylor, Pepperman, and Anker for the non-Euclidean setting for symmetric spaces. Then few name Colling, Meda, Mosheri, and of course Cyan and Thangavalu proved this LP boundedness for pseudo multiplier, which is kind of more general version of than free multiplier. And my advisor here, Ruzhansky, also have many results in this setting for compactly group, for nilpotent, for gradually groups, and other setting. So despite of having LP boundedness, so many results in the LP-LQ boundedness somehow is not studied much in the past. So although in 1960 in the same paper which appeared in Acta Math, it's a seminal paper in this direction. So Hormender gave this condition on the symbol. If symbol satisfy this condition, then A can be extended from LP to LQ, and this theorem is recently extended to many different settings by Ruzhansky in collaborator. For example, Akhil Nur Sultano, and Ruzhansky extended it to compact homogeneous spaces, and more generally, and then Majid they extended to compact quantum groups, which we study in one of the plenary talk, compact one by Sotanu Roy, and then very recently they proved it for locally compact groups. So, and I extended this with Ruzhansky for compact hypergroups as well. So the main technique here to extend for locally compact groups was to prove fundamental algebra techniques. So all these terms we heard in last two talk, like yesterday or day before yesterday by with Gupta. So now let us get back to our main object, anharmonic oscillator. So anharmonic oscillator is given by this operator where delta is Laplace Bell trimer operator. So usually anharmonic oscillators are the is a family of operators, but this operator is a prototype and we call it anharmonic oscillator. And anharmonic oscillator is usually called its red part, and this can be thought as a generalization of harmonic oscillator, but we consider this plus one because this operator is studied by very recently by my collaborator Jaco and Rudhansky and Delgado, and they study a spectral property of this, so we consider this operator due to that. So this harmonic oscillator is quite well known, and many people work on that. It's a very well known. Professor Thangavalu is expert in this, and so so I would like to make some more comment about this. So anharmonic oscillator can be thought of as a pseudo differential operator. Pseudo differential operator is kind of a Fourier multiplier where the symbol not depend only on psi but also depend upon x. So this can be thought of as a well quantization. I will not explain it too much because I don't have time, but it's just to give a connection to different field. And this anharmonic oscillator also occur as a symbol of sub-Laplacian on Heisenberg group. We just heard by Baxi. And so Heisenberg group is a two step nilpotential groups. This also occurs this also appear as a symbol of in the case of three-step nilpotential groups, which are the Engel groups and Cartan groups. And all these connection can be found in this paper. So, okay, so it is well known that the eigenvalue problem for the harmonic oscillator is completely settled, but despite of many effort, this eigenvalue problem for the anharmonic oscillator is still not known. But what we know that this anharmonic oscillator is a compact operator on L2M. So spectral theorem, we can get a eigenfunction consisting of the basis which will be basis of L2Rn, and we do know the corresponding eigenvalue by lambda j, and we have the eigenvalue counting formula which we will use later. So this is the estimate, asymptotic estimate for the eigenvalue counting formula for anharmonic oscillator, which is given by this formula, and this can be derived using something called Weil harmonic calculus, and you can find this in paper of Toft, and this anharmonic oscillator and this asymptotic formula can be derived in some good techniques by this book. Okay, so now we will explain some Fourier analysis using this. So we have eigenfunctions. So using the eigenfunction, we can define the Fourier transform. So Fourier transform is bijective homomorphism from the space C infinity. C infinity is defined as the intersection of all domain of the all iterative power of the anharmonic oscillator using this. So here we replace in a usual setting we have exponential. So here we replace the eigenfunctions of the anharmonic oscillator is the usual setting when we have eigenfunction expansion. So we define like this, and then to have we need some estimate. We need some inequality like Hofstadter inequality and other things. For that we need some weighted space on the dual space. That is, in this case, dual space is on S or iron in N. So on natural number we have weighted LP spaces. So let's define the weighted LP spaces like this. Is a usual, but we need here weight condition. Okay, extra weight because we don't know, and these L infinity norms are bounded here. So we don't have any problem with that. So having these spaces, so we define the Hofstadter inequality. So we say the Fourier transform is bounded. Okay, by the Fourier transform LP function. So now the analysis I presented here can be has been developed in more general setting by Rudhansky and Tukmazambetov in these two papers. And this is the recent paper we got result for more general version of this what I will present here, and with some application to PD as well. So now the main inequality in this, the technique we adopted is the technique of Hormender itself. So the first inequality we prove here is a Pele type inequality. So the classical inequality, Pele type inequality, was proved by Porturas for little Pele, and then Hormender proved it for Rn. So what it says if you have a positive function phi on Rn, it satisfies this condition. So you get so this is LP weighted LP bound. You get this one between P lie between 1 and 2. Now this inequality was extended by Tuzansky and collaborator and by Johan, and this inequality is kind of very useful for a different purpose, not only for LP-LQ bounded Fourier multiplier, but also to obtain Hardy-Dayton-Boode inequality for groups. And especially in this paper of Johan, he proved sharp Hardy-Dayton-Boode inequality, and also derived many interesting things in contrast of quantum groups. So this is the version of Pele inequality for anharmonic oscillator. So if you take a positive sequence and it satisfies this property, so we have this estimate, and all the result which I will present here can be found in this paper. And this is kind of a part of that paper. We have more things in that paper. So the second inequality is the Hausdorff-Young inequality, and how we get this. So we have Hausdorff-Young. So we have Hausdorff-Young inequality, and then we have Pele inequality, and we do interpolation between these two, and we get Hausdorff-Young Pele inequality. So for example, if you see if B equal to P prime, then you get Hausdorff-Young inequality. If B is equal to P, you get Pele inequality in this setting. So now we apply this inequality to get LP-LQ boundedness of Fourier multiplier. This is the main tool in this setting. So we define the Fourier multiplier in this setting also. Instead of Euclidean Fourier transform, we have now AKL Fourier transform using the eigenfunctions of anharmonic oscillator, and then we get this is our main result here, that between this range P and Q, between this range we have if the symbol of Fourier multiplier satisfies this property, then A can be extended from LP to LQ. And this is the main result. Using that, we prove a spectral multiplier theorem. So it says if P lies between this range, then you consider if decreasing function from 1 to infinity. I consider from 1 to infinity because the spectrum of anharmonic oscillator lie from 1 to infinity. So that's why. And such that it wants at infinity, then the LP-LQ norm of this spectral multiplier of anharmonic oscillator is dominated by this quantity. So proof is quite simple. I will explain the proof. So it is easy to observe that this spectral multiplier is a Fourier multiplier with the symbol phi lambda j, and so we apply the previous theorem to get this estimate. Now it's matter to estimate this inside term. So what we do, we obtain some for eigenfunctions using some known results for a more general setting in Weil-Harman calculus, and then we plug up this inside the last inequality, and then we get this. Now to estimate this term, we use Weil eigenvalue counting formula, and that's what we done. So now as a corollary of spectral multiplier theorem, we get the boundedness of negative power of anharmonic oscillator. So it's bounded from LP to LQ if M is greater than this quantity. In particular, it's bounded on L2. So now as a applications of this, we get Sobolev type inequality by choosing Sobolev type estimate by choosing the function P. In particular, if you choose 1 upon U A minus B, then apply this on the spectral multiplier theorem. So we get here A power B minus A F is less or equal to some constant which can be which will be finite. You can prove, and then we get as a consequence of this, we get this inequality, normal inequality, and if B is equal to 0, so this is kind of Sobolev type estimate. Okay, sublow space related with anharmonic oscillator, of course. And now we also derive some time asymptote for solution of the heat equation. So first one, we consider the heat equation related with anharmonic oscillator. So instead of Laplacian, we have here anharmonic oscillator. So this is the solution. It can be checked. This is the solution of this initial value problem. So now by choosing this function phi as t power exponential power minus tu, we get this estimate using the spectral multiplier theorem. And now using the simple calculation, we can calculate the supremum over all this, and the supremum turns out to be this quantity, and then plug up these full things here, and you get LQ bound of this, which bounded by this number. So we get a time asymptote of the solution of the heat equation in this setting. And that's all. I think I am not over the time. Thanks for your attention.
Oh, thank you for that quite interesting talk. Let's see if we have any questions from the audience.
So in the last slide, you gave some heat kernel heat estimate, right?
Yes, it's a kind of time asymptote for the solution of the heat equation. Yes.
Yeah. So do you have any kind of heat kernel estimate? I mean, the kernel, the alien heat estimate, Gaussian type estimate for kernel?
No. I don't have. Yeah, I don't have.
What are your main techniques?
Techniques are here actually developed by Hormender, but later we for a spectral multiplier theorem we derived this using Weil-Hormender calculus, which I did some little bit cheating here because I don't explain anything about Weil-Hormender calculus because I don't have here time. So I just hide all these things because I don't have time to explain those things. This is the things which is area of his own study. So, so I did little bit cheating and present you direct the result. It's not behind the recipe, what is behind going on. So it looks simple, but it uses lots of various known results which are developed in very general settings, especially for a spectral multiplier theorem. Up to Fourier multiplier is quite easy, standard techniques which are developed by Hormender.
Any other questions? Okay, so if there's no other question, we'll thank the speaker again, Vishvesh. Thank you.